For today's webinar, we have Dr. Anoosh Shamsabadi discussing about the soil foundation, soil structure interaction, and ground motion selection for seismic design and analysis of bridge structures. To briefly introduce our expert speaker, Dr. Anoosh Shamsabadi, he has actually over 33 years of experience in earthquake engineering. For the last 29 years, he served as the Senior Bridge Engineer for the Office of Earthquake Engineering at California Department of Transportation, otherwise known as CALTRANS. And over the last 3.5 years, he was serving as a Supervising Transportation Engineer for the California High-Speed Rail Authority. As of now, he is serving as the member of Technical Advisory Panel for different projects, including BART and High-Speed Rail. And he's also taught in a number of national and international short seismic courses. So he is an expert in the field that he is presenting in today. We are extremely honored and pleased to have him as a speaker. And we did check out his presentation, and it's extremely engaging. So hopefully, without further ado, I'll bring this over to Dr. Anoosh, and he will be able to get started with his presentation. Okay. Dr. Anoosh, can you hear me?
Yes, I do.
Okay.
Okay, well, thank you very much for the introduction. The topic of the presentation is soil foundation and structure interaction and design and selection of the ground motion for a particular structure of interest. I want to first do my disclaimer. I don't represent anybody. I don't represent any organizations. I don't work for CalTrans anymore, neither for High-Speed Rail. And I think on the website it's indicated that I work for CalTrans, but I'm retired from CalTrans. I also have a couple of acknowledgements that I want to make through my interaction with Dr. Farid Gahari from UCLA and Mr. Farid Novari from SE Solutions that I worked very closely for a number of years, and I've learned a lot from these two gentlemen. So thank you very much for your support. In particular, we will at the end discuss about RICHCREST earthquake and what we have learned from RICHCREST earthquake and application of the ground motion with respect to engineering, and what is it that structural engineers need to do before you start doing your time history analysis. So we will discuss time history ground motion, three-dimensional global bridge modeling, soil foundation structure interaction, and at the end we come up with a conclusion.
Dr. Anoosh?
Yes.
Sorry to interrupt. I believe you forgot to show the screen. So right now it's still at the title screen.
Oh.
If you can just activate your screen, just the play button should be good.
Is it shown now?
Perfect. Yes.
Okay, sorry about that. By the way, can everybody hear me? I forgot to say that. Can everybody hear me? If you cannot, please raise your hand. Okay. So the outline of the presentation, time history ground motion, three-dimensional nonlinear global bridge modeling, soil foundation structure interaction, and then we're going to come up with a conclusion. So what do you do when you have a typical structure versus a complex structure, and what is it that you need to do in order to develop the ground motions, and how many sets are required? Typically for complex structures, its community understands that we need to do about 11 sets of time history motions, and for standard structures, typically 7 sets of time history motions if it is required. Just keep that in mind. For typical standard ordinary bridges, 2, 3 span, 4 span bridges, we don't use time history depending on the location and importance of the bridge. We use response spectra, but this presentation is all about time history and ground motion. So complex structures like Golden Gate, Vincent Thomas Bridge, Samoa Bridge, these require time history analysis. Structure like MELOLAND, single 2-span, single column, Painter, 2-span, 2 columns, and Brown Road Bridge. Typically, we use response spectrum, but we have recorded motion on these structures, and we want to examine what we learned from these structures and what is it that we need to do for future structures. So ground motion parameters. As a structure engineer, you need to design structures that resist ground motion. So as a structure engineer, you need to understand seismic source and attenuation relationship, not in detail, but understand what is the difference between shallow crustal earthquake as far as seismic ground motion, intraplate earthquakes, and subduction zone earthquake. So I don't expect any structural engineers to be able to generate ground motion, but you need to understand characteristics of these ground motions, because after all, you're the one who designed the structure, doing the analysis, and it is important for you to see where the structure is located, because the ground motion that you get from geotech, you want to understand if they deliver to the right ground motion. Another way, if you're in a subduction zone like Northern California, you don't want somebody to give you a ground motion from shallow crustal earthquake. So that's why it's important to understand the seismic source and what kind of attenuation relationship is used to develop this ground motion. If you have a structure in a subduction zone and geotech is giving you a ground motion which attenuation is based on shallow crustal earthquake, as a structural engineer, you need to ask why are they using a wrong relationship. So make sure you understand enough about this attenuation relationship. NGA West 2 ground motion prediction equation and NGA East are already developed and they are in production. As a matter of fact, just a couple of days ago, I got the NGA East and also subduction zone spreadsheet that can develop the ground motion for you. Amplitude of the ground motion is important. PGA, PGV, PGD, which is the ground motion acceleration, velocity, and displacement. Another way, if you look at the figure on the right side of the screen, you can see example of what, when we talk about amplitude, for example, PGA of 0.52 GVR. That would be like example of the amplitude. Also, you need to look at PGV and PGV, which is calculated upon integration of this acceleration time histories. Duration of motion is extremely important. You want to make sure that you pay attention to the duration of the motion, because duration of the motion is the one that causes most of the destruction. Another way, a lot of cycles in the motion. For example, if you have structures that are sensitive to energy dissipation, duration is important. If you have liquefaction issue, duration is important, because the longer the duration, the more you're prone to liquefaction. It's not only the PGA, it's actually duration of the motion. Frequency content of the motion, of course, is very important, as you will see later on. When we looked at the RICHCREST earthquake, that's where actually I noticed that frequency of the ground motion is extremely important. Energy, that's the seismic, I'm talking about seismic energy demand. How much energy ground motion is inputting into your system. Very important. The way you look at energy content is looking at the duration of the ground motion by using what we call Eris intensity, which is very simple to calculate. And that's basically energy demand into your system. And as a structural engineer, you want to see what kind of energy absorbing capability your system has. Is it able to handle the seismic energy that you input into the structure through these ground motions? So very important to understand the seismic energy demand. So here is an example of the few ground motions. For example, if I look at the Rinaldi motion, which is from 1994 Northridge earthquake, you get a PG of 0.87. Duration of the motion is only 20 seconds, but it has a very high PGA. If you look at a motion from Northern California, the PGA is 0.51. The duration is 40 seconds, and it has a lot more cycle than you see in the Rinaldi motion, even though Rinaldi has a big pulse, but the frequency content of the motion may not be as big as impact, it may not have as big of an impact as Saratoga motion. Look at Chile earthquake. PGA is only 0.37, but my God, look at their velocity and displacement content and duration of the earthquake. For example, for Rinaldi, you get PGV, which is a peak ground velocity, is only 58. Saratoga is 16. Chicxulub is 103. If you look at the displacement for Rinaldi is 16 inches. Saratoga's about 6.5 inches. And if you look at Chicxulub is almost 166 inches. So these are the things that you need to look at as a structural engineer. You want to look at your response spectra, duration of the motion, and your ground motion parameters. By looking at this actually time histories, you should get a feeling before even you do the analysis what you may think this is going to do to your structure. So when you run the analysis, you want to make sure that what you run against what you input, it makes sense to you. So that's really the message I'm trying to send. As a structural engineer, these are the parameters that you want to look into before you start doing analysis. Another way, when you get a time history record from engineering seismologist or from geotechnical engineer, as a structural engineer, look at the plot and try to understand what this may do to your structure, and is this the right motion that you want to use, or is this located on is it on the right location? Another way, like I said before, if you're working with a subduction earthquake, you want to look at the motions that are very long, not something like Rinaldi or Saratoga, vice versa. So when you do your modeling, obviously you need to pay attention to your boundary condition of the bridge. As you can see, sometimes, for example, in this case, we have restrainer which are supporting the bridge during the seismic event, and you have a rail which is sitting on the top of the bridge, and now bridge is supposed to support the rail, but also is an important boundary condition on the bridge. So you need to consider all this when you develop your global model. Another way, you may develop a detailed global model, but you want to make sure that your ground motions are correct. So when you doing solid structure interaction, basically that means a global system. You have an earthquake motion at the rock, you do your propagation, you bring the motion to the foundation level, you get a free field displacement, you impose the free field displacement on the foundation, and then you get a response on the foundation. This response can be expressed in terms of velocity, in terms of shear, moment, and displacement as a function of time. So now when you have, for example, 7 or 11 sets of motion, you have to look at all these time history for all these responses and come up with some kind of average or make a judgment how you should design the structure. Now, the structure could be supporting either rail or it could be supporting just a regular traffic, but it's still doing the analysis as far as seismic is the same. So if you have, for example, this slide shows not only the global for a typical highway, but also if you have a rail on the structure, what is it that you need to do? Basically, you need to develop your nonlinear solid springs, and depend on complexity of the structure, you come up with a ground motion, and then you need to consider also what the rail on the top of the structure is doing to the structure. Obviously, foundation springs and also abutment springs are the key. So we have a transition zone here that basically will give you the nonlinear springs, and we have done testing that shows how this nonlinear springs will develop. And they're very important in seismic analysis, specifically if your bridge is not too long. The boundary condition from the abutment plays a significant role in the response of the bridge. And then, of course, what kind of motion you will be using, which we discussed earlier. So we've done a lot of testing in various universities. We've done a test in Utah, testing transition zone for high-speed rail and also for high embankment. So here is a test setup with no backfill. This is the abutment. These are strain gauges to measure the pressure. This is the backfill with the compaction in place. This is a system pushing the backfill. This is a typical highway seat of abutment, and you can see the back wall is designed to break during the seismic event and push using the actuator push into the abutment. This is looking at the abutment backfill after it's been pushed. You can see how the soil heaved, and we develop multiple cracks as a function of push into the abutment. These are all static tests using actuator, but also we've done a dynamic test at the University of Nevada, Reno, Dr. Saidi, and this is a dynamic test for the abutment. So here is the video of the test. I don't know if you can hear the noise in the background, but there's a noise with the shake table. So now the shake table is going to hit the back wall. This is basically, that's your back wall, and that's the soil. This is actually a third run. We've already run this a few times. This is a third run. So again, this is the backfill, and this is the bridge deck hitting the abutment during the seismic event. And that's what we have. So as a result of all this, we looked at all these tests, and we came up with the abutment backbone curves and equations. I'm just showing the highway, the test for the highway backfill. So this test was done in UCLA. One was, and the rest of them, they were done at Bill University in Utah. Once we plotted all the test data, we developed our hyperbolic model to come up with the equation to predict the nonlinear backbone curve based on experimental data and also analytical model. So we have a good model how to predict this nonlinear backbone curve, which are extremely important in developing boundary conditions for the bridge. And the test result and also analytical result shows that if you have a nonlinear backbone curve for a zero skew, if you multiply that by a reduction factor R as a function of skew, it would be basically exponential function shown here, which is e to the minus theta divided by 45, theta being the skew angle for the bridge. Just get a feeling for this number. For example, if you have a 30-degree skew, your capacity, abutment capacity dropped to 50%. For example, here I got capacity of about 30 kips per foot. And if I multiply that by e to the minus theta divided by 45, I'll get this green curve, which is the backbone curve for the 30-degree skew. We have published ASE journal papers. If you're interested, just look at the abutment ASE journal paper. You thought my name, I have other co-author, and you can see the papers. So summary of the equation, very simple. Basically, your force function, it would be in terms of hyperbolic model, it has two constants C and D, and the constant C and D, easy to calculate. The values are given. And this is a simple equation how we calculate the ultimate, which is this point, and you calculate the average stiffness, which we call K50, and that's what these are the equations. Very simple. I mean, you can do this in a spreadsheet like in 5 minutes. You can develop based on the simple equations the nonlinear backbone curve. This is just like PY curves that we have from NSOFT and others. This is just another PY curve that is for backwall. So if you look at the new SDC, these are the equations in SDC 2.0. They're based on all the tests that we have done and this analytical model that I've showed you. So the F ultimate, it would be the simple equation times, and then if you multiply that by R reduction factor, it will give you the F theta, which is the skew angle. Very simple. There's no magic. So here is the example of the time history analysis with the rail sitting on top of the bridge using time history. So you can see the complete model. By the way, these are what we call direct model. there are two types of model when you do analysis. One is substructure model, which you get rid of your foundation using a 6x6 stiffness matrix. These are old. We don't do that anymore. Almost everybody that I know of these days, they are interested in doing this for detailed seismic analysis using direct model, meaning your foundation, pile cap, and everything, including the superstructure, should be included in your global model. So you specify your nonlinear spring. Here at the foundation, you impose the motion and basically get your result. So what do we do when you have a complex structure? Either depending on what organization or what criteria you look at, you can use either 11 or 7 sets of time histories. So what do you do if you have a fault rupture? Or even if you don't have a fault rupture, you need to look at 3 component motion, which is fault normal, which is this motion right here. Fault parallel and fault vertical motion. And also you need to look at the fault rupture. And in particular, if you have a rail, it becomes very important that you look at your fault rupture as well. So when you do these time histories, you need to look at the uncertainty in the fault location. And also you need to look at the fault rupture mitigation. What is it that you need to do for your mitigation? Now you can use either isolation or whatever technique you have, which we're not going to discuss here because this is mainly discussing time histories. So, but if you have a fault rupture, what is it that you need to know? As you know, rupture is not a one line, it's just a zone that you need to look into. So you want to make sure that you place the fault at different locations along the structure and analyze it bend per bend and see what might give you the worst scenario. So these are examples of the fault rupture from rail and fault rupture for highway bridges. You can see what rupture is going to the structure. Therefore, is a displacement that you need to consider. It's not just a vibratory ground motion, but fault rupture displacement that you need to consider, just like it shows in these 2 slides. Also, when you look at the fault rupture, this is from RICHCREST earthquake. So you can see fault rupture is not only running for bridges, but also for other infrastructures such as rail. And you can see here how fault rupture has shifted the rail from left to right, and also fault rupture is running right across the rail, and you can see the bend in the basically rail as a result of fault rupture. There are other details. These are all from RICHCREST earthquake. You can see again what fault rupture has done to the rail. Spikes coming out, of course, the movement, and also other underground structure, breaking pipelines, water lines, gas lines. So when you look at fault rupture, or when you want to do earthquake analysis, if you have a fault rupture, you want to make sure that if rupture is in the vicinity of your project, you need to look at the fault rupture issues too and impose fault rupture into your time history analysis. The way we impose fault rupture, basically you come up with a vibratory displacement ground motion, and also you come up with a permanent fault rupture displacement, and then you impose the permanent displacement into your time history, and therefore your time history is going to look like this on the one on the bottom. So the time history that you need to use for the structure that are located close to a fault or running across fault, you have to impose the permanent displacement into your time history. And like I said, this is the displacement that you use. The slide on the right, it shows basically a time history record from Chi-Chi earthquake. And by imposing a fault displacement into the record, you can see what the record is going to look like at the end to be implemented for any particular structure that you're interested in. So the way you do this, basically you impose a sine function at the location of the pulse, and you integrate this sine function within your acceleration time history, and it would basically give you a velocity. It adds your velocity pulse, and also it adds your displacement at the end. This is the established procedure that has been used on various projects. I'm not going to name any particular project or any criteria for any particular project, but this has been already implemented in a couple of projects that I was involved with already. So, but now developing global model these days is not an issue. I mean, there are new techniques now with this computer age that we can develop very sophisticated computer model and look at things in detail. This is an example of what we call CIM, which is the SIM, which is Civil Information Modeling and Management. This is done actually through MIDAS. It's an independent software. It doesn't depend on AutoCAD or MicroStation. It's a software that is developed by MIDAS. And you can take the set of bridge plan. And with this set of bridge plan, actually, you can develop your full 3D bridge model. And it could be like even a continuum model, like not really like a beam spring model, but a continuum model. That shows also all the rails and everything. As you can see, on the bridge with isolation casing and so forth. So all of this can be included in your model. And here is an example of that model. So with this model, I'm trying to show the fault rupture. I'm assuming they have a fault rupture located at this bend, in between this bend and this bend. You can see these are all supported on type 2 shaft with isolation casing, and this portion of the foundation is supported on pile group. So the structure could be combination of, depending on the structure location. If it's running, for example, across the river, you may want to have combination of shaft and pile group. In this case, this is combination of shaft and pile group, and we want to see what happened to it as we impose the fault rupture. So if I impose a fault rupture and vibratory ground motion, you can see I have a ramp function here with my history that is basically pushing into the bend in one direction and pulling in another direction. And that's what happened. And you can see how superstructure is actually twisting. This is a closer shot. So I have the vibratory ground motion and a fault rupture imposed at this bend and this bend. Now, if I isolate the structure now, then you can see through isolation, nothing is happening to the superstructure, but you just need to make sure that you design the structure or the substructure such that it would take the displacement required by fault rupture and vibratory ground motion. You just need to provide adequate seat or some kind of isolation that would basically is capable of handling your demand. Now, so far I talked about the general ground motion and what is it that you, as a structural engineer, what is it that you need to consider? How do we know what we're saying or what we've done is correct, or we can make sense out of it? So we looked at many instrumented bridges, including complex structures, just like I showed here. This is a CALTRANS bridge located in Northern California, Eureka Samoa Bridge. The bridge is 2,065 feet long, 34 feet is the width of the bridge. It was constructed in 1968 and it was retrofitted in 2002. So we basically, the recorded motion that we will show you for the analysis that I'm going to show you is done based on after the retrofit was completed. So here is, I'm going to start with the simple instrumented bridge and see how we were able to model this bridge and develop and come up with a response that matches the recorded motion. Two bridges that we looked at is MELOLAND and Painter Street. Excuse me. So these are the seismic instrumentation. We have done extensive testing on the bridge, including the abutment test. So we drilled behind the abutment in order to capture the properties of the abutment and see how we develop nonlinear backbone curves for the abutment, because like I said, abutment plays a significant role on this type of structures. And here's another one, Painter Street, Northern California. That's on south, and that's in south MELOLAND. Painter Street located in Northern California. That's a single span, two-span single column, and that is a two-span, two-column bed. So we've done ambient vibration tests on these bridges. I'm just going to show you one of them, MELOLAND. So here is one of the ambient vibration tests, which was done by University of British Columbia. And I was there when they did the ambient vibration test. So here is the recorded ambient vibration result. And here is a MIDAS model, including all the foundations using a direct model. Here is another twisting ambient vibration. And here is a MIDAS model. Another way, before we start developing these time history models, we wanted to make sure that our model is calibrated against this ambient vibration, so we get a good sense of basically the periodicity of these structures. And so if you look at MELOLAND, I'm just showing one of the instrumentation result. Here is basically channel 9, recorded versus calculated. So recorded motion is channel 9 versus calculated motion. They run on top of one another right here. And again, because we had a very good model of the abutments, we were able to capture the response of the bridge. Also, the pile cap springs played a significant role. So one thing about these pile caps, a lot of engineers, they ignore contribution of the pile cap. Honestly, when we're looking at these instrumented bridges, including the Samoa bridge, which actually pile caps were sticking up above the mud line above water surface. The pile cap, mass of the pile cap, was very important in basically matching the recorded data versus calculated data. For MELOLAND and Painter Street, not only the mass of the pile cap, but also this nonlinear spring attached to the pile cap, they were also very important in capturing the response of the bridge compared to the recorded data. So here is a Samoa bridge. I'm looking at channel 10 and channel 8. This basically channel 8 is recorded at the bottom of the column, channel 10 at the top of the column, and we're looking, these are in the transverse direction, which are the key or very important in seismic analysis. Here is the detail of the model. So we impose nonlinear springs. And honestly, I did not play with this nonlinear spring at all. I just look at the source profile. There is not enough time for me to show the source profile. But we just looked at the source profile, developed nonlinear spring, just like we do for typical bridges. Impose and attach the nonlinear springs to the piles, impose nonlinear time history motions. Like I said, the pile caps, mass of the pile cap was very important in capturing this response, and also crack movement of inertia, assigning to the columns was also important. And here is the response of the bridge. Only I'm just showing only channel 10 in a transverse direction. If you look at this is the displacement time history recorded versus calculated. If you look at two peaks, basically the period of the peak to peak is about 1.48 seconds, and that matches actually the period of the structure in a transverse direction. And that's what I'm showing, the mode shape in a transverse direction with a period of about 1.48 seconds. Let's call it 1.5 seconds. That becomes important when we were looking at the RICHCREST ground motion, looking at these periods, and see, as I'm going to show you later on, if we excite this bridge with RICHCREST earthquake, what would have happened to this bridge, rather than this motion from recorded motion from site. So here is the animation of the bridge using time history, and this one is just looking at one of the piers. This one. Okay, so far we talked about bridge instrumentation and what we did in order to calibrate our recorded data versus our analytical model. We didn't use any continuum model. The models are not really too sophisticated. They're just beam spring models. And I really think this beam spring model is the best to model bridges. You know, because we know what to do, we understand them, and we work with this many years. So my recommendation is, based on my own experience, beam spring model is the best to go, and direct model. You know, I don't do substructure model. Another way, I don't break the structure to superstructure and also model the foundation separate. These days it's easy to do it. Actually, I think it's a lot easier to do the direct model than do a substructure model, because when you do a substructure model, you have to build all this foundation model separately, analyze them, and then come back and see if they work or not. But with the direct model, your foundation already included in your model. If you need to do pushover analysis, whatever you need to do, you already have everything in your model. All you need to do is just separate and go. So let's talk about what we learned from RICHCREST earthquake, and what is it that we need to do from what we learned from RICHCREST earthquake in regard to ground motions. So here is an instrumented bridge. These are the instrumentation. I'm just showing instrumentation. We looked at instrument number 7 and number 4 in a transverse direction. The bridge is located about 14 miles to the kind of west of the main rupture, magnitude 7.1. There were 2 earthquakes, magnitude 6.4 and 7.1. We're just looking at the magnitude 7.1, not the 6.4. So that's what we're looking at. In particular, I looked at this motion, recorded motion on Brown Road Bridge, and also imposed another motion with a very high directivity, which is located at the end of the fault with the high directivity, and see if the bridge was located here, what would have happened to the bridge rather than located 14 miles to the west of the fault. So here is a little bit more detail of the bridge. In order to understand the behavior of the bridge, we wanted to look at some detail of the bridge. Channel 7 and channel 4 are located at bin number 3. Bin number 3 are fixed to the pile foundation. Bin number 2 and bin number 4 are pinned. And as I will show you later on, you can see this bridge. If I would have looked at this bridge before, again, that's my personal opinion. I'm not saying what should have been done on this bridge. But if I would have looked at this bridge as part of the screen, I would have thought that this should have been retrofitted. But it's interesting, nothing happened to the bridge during this earthquake, magnitude 7.1. Nothing happened to the bridge. Why? And we will look at it. It's got also 45 degrees skew. And it was constructed in 1966. At that time, I'm not even sure if seismic was considered or not. I'm not sure. Here is more detail of the bridge. 42 feet is the width of the bridge. So bin number 3, as I said before, is fixed to the pile cap and the foundation. This is just a schematic. This is bin number 2 and 4 are T connection. You can see the detail for columns. Number 11, total of 24, but it's got only number 4 spiral and 12 inches pitch. So I would have thought this should have probably been retrofitted. Also, this is the detail of the foundation piles, 18-inch diameter foundation piles. Number 6, total of 4, again with minimal confinement. And here is the detail of the pile, column sitting on the pile cap. Pin connection with 4 number 11 dowels extending from the pile cap into the column. Abutment, very important. It's a monolithic abutment. 9.5 feet is height of the abutment. Therefore, you will get a lot of capacity, a lot of resistance from the passive pressure from this abutment. And that's why we've done a lot of testing to make sure that we understand the behavior of all these abutments. So here is recorded motion, free field, channel 4, and channel 7. So free field means somewhere located in the ground. We have a motion which has nothing to do with the structure. Then we have recorded motion at the top of the pile cap or bottom of the column, and we have recorded motion at top of the bridge. My God, they're all on top of one another. And that's why when team of CALTRANS earthquake engineering, they looked at the bridge, nothing happened to the bridge. Why? With this 7.1 magnitude earthquake. If you look at initial part of the time history, maybe 15 to about maybe less than 25 seconds, you can see there are, by the way, the red is for bridge deck response. You can see something is happening at the early stage of the earthquake. These are at very high frequency motions. So here, I kind of try to zoom in a little bit here. So I'm zooming in from 15 to maybe about 65 seconds. And then I zoom in more to see if we understand what's happening with this motion. When we looked at the period, fundamental period of the motion is about 0.32 to 0.35 seconds. Depends whose model you look at. But overall, a little bit over 0.3 seconds is the duration of motion. The period of the bridge. And when you look at the period of this motion has a very long period. Therefore, the bridge doesn't feel this. The bridge goes with the ride with the earthquake. That's what happened. So when we looked at this, when I decided, well, why don't we shake this with different motion and see what happens here? What if I shake this bridge with the motion right here? This is one of the strongest motion with a very high directivity and large parts. So when we look at this motion, actually this motion matches the recorded motion, the calculated, I don't have recorded motion here, but calculated motion versus recorded motion or versus input motion are exactly the same. Very, very minor differences, but almost they're identical, again, because this is a very high period motion. Therefore, it's not doing anything to them. So that's what I'm trying to say. You need to understand what motion are given to by geotechnical engineers or engineering seismologists. You need to communicate with them and make sure they understand some portion of the structure behavior that, or you want to make sure you understand what excites your structure. So in this case, honestly, if I want to design a bridge in this zone, I would have said, if I wouldn't have this ground motion, I would say, you know, I want to use this motion to design my bridge. Well, this motion is not doing anything to a particular bridge, to a particular bridge that I may want to design. So if I'm designing bridges, short span, typical standard ordinary bridges, this motion is not doing anything to the bridge, unless you use some kind of response spectra from this motion and say, okay, for a given period, I need to come up with a smooth response spectra and design for using response spectra, not time history analysis. Then I thought maybe it is characteristic of these type of bridges, which are monolithic abutments, and maybe because of their configuration of a structure, having deep abutment back wall with participation in water soil capacity, maybe that's what is happening to these structures and they're not moving. Well, I had a calibrated model from Painter Street. So I had a motion from Painter Street, 1992 Cape Mendocino earthquake with magnitude 6.9, which was even less than magnitude 7.9. So I decided I'm going to shape this structure with this motion and see what happened. If I would have used a different motion, what would have happened to this structure here? Also, please notice that these bend number 4 and bend number 2 are pin connection. Column pile cap are pin connected, but bend number 3 is fixed. And well, I'm going to show an animation and see how the pile cap is behaving or foundation is behaving with respect to this fixity, which is also very important for structural engineers to know because of foundation capacity protection. So if your columns are fixed to the pile cap, that means, sure, all your structural engineers know that there will be tremendous load in terms of moment and shear carried to the foundation. So that means foundation has to be designed by either, if it's a pile group, it has a different criteria rather than the shafts, by over the strength design for shear and moment. So here is the animation. Check the pile cap. You see on the fixed, pile cap is moving around. Also foundation is moving around. If I zoomed in here, actually foundation moves around a lot. But if I look at the pin connection, you can see nothing is happening actually to the pile caps and the piles. And that really is the preferred design if you don't have to use, if you don't have to fix, you don't fix it. That's why many bridges with multiple columns, they try to pin the column to the top of the pile, to the top of the pile caps. Or if you have type 2 shaft, also that's something that you may want to consider, pinning the columns into the pile shaft or into the pile caps. But if it's a single column, you don't want to do this. But for multiple columns, you can do this. So now, this was shaken with the Cape Mendocino earthquake, and this is what I'm going to show you. This is the result. So you can see the input motion is the black line, and the red is the output. I know the model is good because we were able to match recorded data for the RICHCREST earthquake, and we really paid a lot of attention developing this model in detail. With basically 2 different models were developed, completely independent, and we both came with with almost identical result or conclusion for RICHCREST. But then I extended the model and I developed this model for various ground motions to understand what is happening in these ground motions. It was actually after RICHCREST earthquake that I noticed, hey, as a structural engineer, you really have to pay attention to the type of motion that you're getting, understand the motions, and if these motions are applicable to your particular structure that you're trying to analyze. And also, we decided to shake this other structure with Brown Road Bridge motion, with RICHCREST motion, and see what happened to other bridges. What would happen if this earthquake would have had the same motion characteristic but happened somewhere else, or other bridges are located in this zone which were not similar to road bridge ground motion shown with the black line. And this is the response of the Samoa bridge using the recorded Brown Road Bridge motions. And you can see actually the bridge is, you can see the difference between the input motion and the response of the bridge. So again, what I'm trying to say, you really need to pay attention to the characteristic of the motion and characteristic of your structures. Just don't take any motion you get from geotech or engineer seismologists. You need to tell them about the characteristic of your bridge. Tell them what kind of period your bridge has, what kind of fundamental period it has. Talk about a little bit about the stiffness of the bridge, span length, so they would give you a proper motion that fit your needs. Also decided to shake the motion, to shake some very long period structure with the Brown Road Bridge or with the RICHCREST earthquake and see what would have happened. This, let's say you have a bridge located in LA and you get an earthquake similar to RICHCREST, or if you have a bridge similar to this in the vicinity of RICHCREST area, what would have happened to this bridge? You can see the black line again is the input motion from the RICHCREST earthquake. The green line is the response at point A, which is at the deck level, and then of course the red line is the response at top of the tower at point B. And this is basically the animation, again using MIDAS. And again, it's a direct model. Nonlinear solid springs are attached to the foundation. Now you don't see foundation is moving because I'm using acceleration response, acceleration time history, which are relative. Is basically that's why the foundation is not moving. But if I would have used displacement, you can see also as far as animation, you can see that you could have seen that the foundations are also moving as well. By the way, for running time history analysis, you can use either acceleration time history analysis or displacement. If you have a uniform geology, simple structure, not too many variation within the site, you can use acceleration time history. But if you have if the geology varies across the structure and a structure is complicated, then you cannot run this acceleration time history, but you need to use a displacement time history. So this is kind of the conclusion of my presentation. I'm showing this just to show the difference between the various structure excited with the different time history motion. So we have representation of Golden Gate. We have representation of Vincent Thomas Bridge, representation of Samoa Bridge, representation of MELOLAND, Painter, and basically Brown Road Bridge, RICHCREST. So we excite all these structures with a 2019 RICHCREST earthquake and also with the Chichi earthquake to see the difference. These motions are very long period motions. So we'll see what will happen to the long period structures compared to the short period structures, like what we like MELOLAND or Brown Road Bridge. So that's what you're going to see. So long period structure, you can see movement on these standard ordinary bridges which are stiff. You can see this long period motion is not really doing too much. That's actually representation of Vincent Thomas Bridge. It moves a lot because the period is about almost 5 seconds. This is for Samoa. The period is about 1.5 seconds. And of course, these are standard ordinary bridges with period is about less than 1 second, basically almost less than 0.5 seconds. So you can see they don't move as much. But now if you use motions with very high frequency, then you're going to see that you have what we'll see is going to happen to the structure with low period, high frequency compared to the structure with high period. So you can see how these small structures are getting really excited here. Okay, and that's the end of the presentation. I'm going to show you a video of the RICHCREST earthquake. Scientists, seismologists, these are all very involved with developing ground motion, NGA West 2, NGA West, NGA East. That's actually in RICHCREST, just before the magnitude 7.1 earthquakes. That's in the hotel. I've got this video from Professor Bozogna from UCLA. Interesting how, see how cars are moving with their own frequency and different directions. Trees move in the background. So that's a real simulation of the earthquake with I wish there was a bridge structure here that we could see, but that's all we have. So that's all I have. I'll be happy to answer any questions. I didn't want to get in too much into the detail. I didn't know if you wanted me to open a bridge model to show how we did this, but I'm sure it's I'm assuming that whoever is watching this video or in this presentation, they already have a lot of modeling experience, and I'm not doing anything magical. Just attaching nonlinear springs to the foundation, using the beam spring model to develop the bridge models, except the one I showed for the fault rupture. That's a continuum model. And the reason I decided to go with the continuum model for the fault rupture, that's if you need to look at, like, you have a fault rupture, you want to look at cracks, concrete behavior type of analysis. That's the only time you want to use continuum model, but not for global. And that was actually, the reason I did this, because I wanted to use not only the capability of SIM in MIDAS, but that was generated actually with the SIM in MIDAS, but also look at more internal properties, and like I said, like cracking and other phenomena on the bridge. Other than that, beam spring model is fine. So far, anything I've done, either seismic isolation, nonlinear time analysis, beam spring model, direct model is the best way to go. That's the end of my presentation, and thank you for listening.
Hey, thank you, Dr. Anoosh. We're going to take a few minutes to just address some of the questions. I've taken the liberty to put them up on the screen so you guys can take a look, the attendees could take a look. At this point, officially the session is over. So for those who are interested in sticking around, you're welcome to do so. And at this point, you are able to ask questions. So in the control panel as well, there is a questions tab, a chat tab. So if you input your questions there, you should be able to we should be able to address them. And if there is something that we can't get to in terms of the timeline today, we will be Dr. Anoosh will be kind of answering those questions and putting them on the review page as well. Okay, so for right now, I'm gonna have Dr. Anoosh kind of review through the questions I have listed on the screen, and he'll address them one by one. I've chosen 12 questions right now. I think that's about the amount of time that we're gonna have. So, but any other questions, please type them in and we'll address them. Probably, if not today, at least in the next coming with the review pages. Okay. So, Dr. Anoosh, if you could take on the screen, you should be able to see the questions now. If you could just go through them and briefly answer them, that should. I think we can finish off with. I have 3 pages of these, so after the 3rd page, we'll end it off here today.
Okay. I'm going to skip the first one and then I'll come back to it. Regarding the nonlinear backbone curve, how many curves should we develop along the height of the abutment to capture the right soil abutment interaction, knowing that the lateral displacement of the abutment is varying from top to bottom? Okay, beautiful. You know, everybody thinks that and it is true, typically for sandy soil, of course, at the top of the wall, if you assume a wall, at the top of the wall, you get less force than you get on the bottom of the wall, because it's nothing like gamma H times Ka, gamma density of the soil times height of the soil, and times some kind of a K, which is either active or passive pressure. For abutment, that's not the case, because abutment actually behavior looks more like spread pooling, if you will. Is mostly uniform pressure distribution. Remember, it is not only sand, because you cannot even compact the soil with pure sand. It has to have some level of cohesion into it. Basically, it's a C3 soil. Therefore, the pressure distribution tends to be uniform. It doesn't really vary that much with depth. And for all practical purposes, you can assume uniform pressure distribution and develop uniform spring along the height of the abutment. Warning though, for skew abutment, springs may not be uniform along the width of the abutment because it is a function of rotation of the back wall, rotation of the deck into the back wall and the reaction of the back wall soil with respect to the deck. So if bridge is rotating, therefore, on the obtuse corner, you get a lot of passive resistance, so your springs are a lot different than you have on the acute corner. And as a matter of fact, to be honest with you, I'm working on a paper right now to address this issue. Right now, we would distribute spring along the height and along the width of the bridge if it is skewed. If it is not skewed, and you use it depends if you use a frame element with one frame, basically you can attach one spring representing the abutments. But if you have a skew abutment, then you have to use multiple springs along the length or width of the abutment. You cannot use a single spring. But I hope that answered the questions. Is it okay to throw away a new print pad with the bridge deck sitting on the abutment and a pillar? Is it okay to throw it? Well, you know, if you have a new print pad, you need to consider it as some kind of a spring in your model. That's a good question, actually, because interestingly, one of the abutment was fixed to the pile cap and the other one was sitting on a new print pad. So new print pad is modeled as part of the bridge global model using spring. So you need to include new print pad. You cannot ignore it. Okay, next question. On the bridge model, you analyze and compare it. Okay, let me see. On the bridge models, you analyze and compare against RICHCREST and Cape Mendocino earthquake. Did you assume full moment release for the column base pin connection, or did you consider minimum? No, it was basically pure pin connection. I did not model. I didn't model the pin as some kind of with a minimal capacity. No, it was not. And honestly, I don't even think it would have made a difference in the result. Even if you would have fixed all of them, it wouldn't make a difference on the result because this whole bridge is going with the motion. Is not affecting the response of the bridge, even if you would consider fixed or pin. So therefore, we did not bother considering the pin, the participation from the pin or minimal capacity from the pin into the model. Okay, let me see. Any more questions? This is all I see. Any more questions? I don't see any other questions. Okay. Okay, so we have made global model. Okay, we have made a global MIDAS model for particular project in India. We are performing response spectral analysis and time history analysis after using nonlinear springs for piles. But the issue is the nonlinear springs do not work with time history analysis or response spectral analysis. Is there any way out? Well, you know, if using the response spectra, of course, nonlinear springs is not going to work because response spectra is a linear system. So if you use any computer software, which I'm not going to name here, you can either specify your linear spring as an average secant spring, or you want to use initial spring, you could do that. But you need to specify a linear spring if you do a response spectrum. Non-linear springs for response spectrum, it doesn't work. If you don't specify a linear spring, the software is going to take it, the one I know of, as your initial stiffness. Or you could go and specify what stiffness you want to use when you do response spectrum analysis. As far as nonlinear time histories, your spring should work. I mean, you should get it. The way you can see if your spring is working or not, you need to go to the link element, nonlinear link element, select your nonlinear link element force and displacement, and plot the time history, and you can see a very nice historetic behavior of the nonlinear springs. That basically, it will show a very nice historetic behavior. So it should work. I don't know why nonlinear spring is working in your time history analysis. It should work. Unless you forgot in your analysis to specify that they should be using nonlinear spring. You've got to be careful when you go to these softwares. It has options. I wish I could show you one in MIDAS, for example. I don't know if this question would have come out. I will show you. You need to make sure that you tell the software that it should select the nonlinear springs to do the analysis. You could define nonlinear springs, you could assign them to the springs and so forth, but if you don't specify as one of the options in the program that you expect the nonlinear spring to kick in, it won't do anything, it will just take your initial stiffness. So that's basically what you need to do. I mean, I don't know what software you use, but I'll be happy to show you later on. And if you want me to show you how to do it, not now, but later, you can send me an email and I'll show you how it works. Okay, so that's next question. Thanks for the presentation. What is your recommendation for pile shafts that are crossing a fault surface? Would it be acceptable to have the pile sheared off? There is no way to provide sufficient capacity against a fault rupture. Well, that is really more of a criteria question. It depends on what kind of criteria you have. I mean, if your criteria says that you have to have a capacity protected foundation, then you need to come up with a design that, you know, either don't cross the fault, avoid crossing the fault, which you may not be able to do that, or you have to do something, you know, it's some kind of ground modification or something that, you know, nothing happened to your piles. It depends on your criteria, and it depends on what owner is expected to do. Next question, can we use conditional mean spectra as our target spectra for time history selection and matching? Well, that's a very interesting question. There are two methods of developing time history analysis in regard to the target spectra. One is the compatible time history motion, which matches the entire spectra, and which is we call target spectra compatible time history motion. Or like it says here, you can use a conditional mean spectra, which means you match all your time histories, 7, 11, or how many you have, you match it for a given period. Another way you can match it, for example, for a period of 0.5, 1 second, or whatever period of interest is, you can match it. To me, for bridges, that's again my personal opinion. I wouldn't use conditional mean spectra because especially complex bridges, they have many periods, many or mode shapes that participate. Therefore, you should not be using conditional mean spectra. If you know everything about the bridge, if you know the fundamental period of the bridge and you want to match the fundamental period of the bridge only, you might be able to get by with the conditional mean spectra. But I don't use conditional mean spectra myself, especially for bridges. I don't think it's a good idea to use conditional mean spectra. Maybe for buildings, but for bridges, I wouldn't use that. Okay, would it be a good idea to cut the time history function into half because at the complete cycle, the bridge returns to the middle, which does not seem to move. Okay, I think that's an excellent question. One other reason, as a structural engineer, you want to look at the time history record before you start using it is the duration of the record. I have been involved in seismic analysis of a bridge in a subduction zone, and I've got one of the motions which are 300 seconds duration because it's in the subduction zone. So if you want to run this model, it would take a long time to run 300 seconds motion with the 300 second duration of the motion. So is there a way to cut unnecessary times into the motions? I really think it is. If you look at this recorded motion, I'm just giving an example. Say from 0 to 20 seconds, you don't really see anything. And then from, let's say, 60 to the rest of the motion duration, you may not really see anything. Why should you include it in your time history analysis? Pre-post processing, computer run times, all this. So if there is a way to cut this duration of the time history, I think you should. And that's why at the earlier part of my presentation, I showed Aries intensity. Aries intensity has to do with the effective duration of the motion. So you always want to look at Aries intensity and then ask the geotech if there is a way they can cut some of the portion of the time histories, except, for example, the effective motion, which is either from 5 to 95% of the energy contained in the motion, or 5 to 75% of the energy contained in the motion. I really think that's an area that needs to be looked at, because as an analyst, I don't like to use these long motions that have a lot of zeros in it, because it's just waste of time and runtime, computer runtime. Okay, next. Okay. What next?
Dr. Anoosh, I think we'll stop there for today, because the questions are coming in a lot. So, and it is 4:20 now, so we'll stop it here. So we want to thank you for taking the time to answer these questions and for the presentation. For the remainder of the questions, Dr. Anoosh, I will send them to you, so that way you have a chance to review them and provide your input. And for those who are, if you're okay with it, some people are asking for your email or some way to connect with you, which actually goes into the next portion. But for today, want to thank Dr. Anoosh and everyone who stuck around to kind of view the session and stick around for the questions. We will be sending the details out and the review pages out. Okay. So thank you, Dr. Anoosh. Okay, so for the last portion of for people who are asking about Dr. Anoosh's email address, he's actually one of our expert speakers. He's an expert influencer, to be exact, and we have something called the MIDAS Expert Network, where we have these webinars as well as opportunities to share and a community to really kind of exchange information, questions, and it's not just related to specific bridges or topics of such. It can be about just the industry in general as a marketing content. So what we are, as an expert influencer, if you have any interest in this and would like to get connected to Dr. Anoosh, we encourage you guys to visit the site and join the network so you guys could get connected with Dr. Anoosh and other expert influencers actually in the network. So we have over 40 influencers, as well as a few of them connecting with DOTs as well and government agencies. So other than that, we would like to thank you again for taking the time to come in and sit in on the session. So we will be sending you the recording with the review, as well as the Q&A that Dr. Anoosh has answered. So thank you again. Have a great day and have a great rest of the evening. Take care. Bye.